So hello, my name is Amelia Holcomb, and I'm a third-year PhD student co-supervised between computer science and plant sciences. And today I'm going to be talking about my work on remote measurement of degraded tropical forests. I'd like to get started by thanking my supervisors, Srinivasan Keshav and David Coombs, as well as the Harding Scholarship funding me for my years here in Cambridge. So, historically, a major topic of environmental policy and remote sensing has been deforestation. But what happens when we think about degradation, where there's partial loss, but the area remains forested land? For example, in the tropics, we see a lot of this with fire, drought, and selective logging. And these causes are becoming more and more prevalent every year, with degradation surpassing deforestation by area in the Amazon rainforest. Degradation is difficult to detect from satellite imagery, but there have actually been some really big advances in this space in the last 5 years, and we've gotten pretty good at detecting it. But where satellite imagery starts to fall short is in trying to quantify or measure the impacts of those changes in any real way. So to think about this problem, we have to understand that the Amazon rainforest has a complex and layered structure, and disturbances can have different effects on different layers of the canopy. But satellites, optical satellites, are just looking from the top. They don't penetrate the forest canopy, and they're largely just measuring greenness, I would say, which can look very similar between regrowing, degraded, and mature forests. And there's just a limited amount of ground data on regrowing and especially on degraded forests. So even if the satellite picks up changes, it can be hard to understand how to interpret them. In fact, we have a hard time using these optical satellites to answer seemingly simple questions like, how tall is that forest? Let alone much more complex questions like how much biomass or carbon is stored in the forest, or how has the understory been damaged through degradation? So right now, our best estimates of the carbon emissions from degradation range from 40% on the low side to 212% on the high side of the emissions from degradation. And these are our best estimates, so there's a huge amount of uncertainty here. Into this mix comes a new sensor, JEDI. JEDI is a laser scanner that's mounted on the International Space Station, and with its 8 beams, it takes samples across the world's forests, washing each location with a laser pulse and measuring the return waveform from the top of canopy, mid and understories, all the way down to the ground. But JEDI is not really ideal either. JEDI is a sampling mission, so it doesn't cover the whole Earth, just individual footprints. And it also has a key limitation when we're thinking about dynamics in forests, like degradation and recovery, which is that JEDI is not very good at measuring change. It doesn't have any regular repeat cycle, so it's not looking at the same place again and again, week after week or month after month, like many other satellites. And it's also a relatively new data set, and it won't be in the sky forever. So looking at long-term changes in forests is difficult. So what we need to do is to get these different sensors working together, each playing to their strengths. And finally, this data set is very large. It's about 65 terabytes of data just for the tropics, with billions of measurements and spatially disorganized data. And we're trying to join this with large, high-resolution data sets from other sensors. And this means that distributed spatial data processing, which is more of an underdeveloped field, I would say, relative to distributed databases and processing of non-spatial data, becomes crucial. So one of the first ways that we got around these limitations and were able to look at forest change was to examine recovery. We took estimates of forest age, which we could get from these long-running satellites, optical satellites, based on the last time that they saw a deforestation event. And we can compare the carbon stocks that were measured by JEDI in forests of different ages. And then this allows us to estimate forest recovery and carbon sequestration rates across broad ecoregions. And we were also able to find evidence of delayed recovery in certain heavily degraded regions. A second way that we can get around these JEDI limitations to measure change is by taking advantage of some irregularities in the JEDI orbit. So like I said, JEDI was not designed to have a consistent orbit, but it did occasionally pass over the same area twice. And sometimes a disturbance or degradation event happened to occur between those two overpasses of the JEDI sensor. And it was detected by another satellite, so we know it happened. And if we could find those times, we could get a pan-tropical sample of before and after measurements of forest degradation, which would include information about carbon emissions, plant area changes, understory and overstory changes, and lots of other variables that environmental scientists are interested in. But this is a needle in a haystack search, and so efficient spatial data processing is key. So from all of the JEDI measurements, which I'm showing here, we looked at just those in the Amazon biome. And from those, we identified about 4 million times when we happened to get a repeat measurement. And of those, a little over 13,000 happened to have a degradation event intervening. And when I put it like that, it seems small, but actually, as far as we know, this is the largest data set that anyone has ever had of before and after measurements of degradation in the Amazon. So we published this as an open source processing pipeline to find these sort of lucky locations where this happened. And with this data set, we were able to first just demonstrate for the first time that JEDI could measure these really small disturbances, which when you think about it is quite incredible. We're aiming a giant laser from outer space and we're measuring really small changes in the forest. We were also able to use JEDI to measure these complex structural changes. So we identified about 20% of burned areas where the forest maintained its original height, but the understory suffered substantial losses. And finally, we found evidence that it might be possible to extrapolate from our data set by uncovering how these measured carbon emissions relate to the changes that were observed by other satellites, like optical satellites. So in this graph, we found a relationship between a disturbance intensity index that's based on optical data alone and the carbon emissions, or the percent of biomass that was lost in the disturbance. So these approaches have led us to some exciting new research avenues and areas of collaboration. First, we've been working with the academic groups that develop these pan-tropical disturbance detection maps to help validate those maps based on our measurements of the changes that actually took place there. Second, we've been working with nonprofit groups that are helping to assess global progress towards conservation and towards land use change emissions reductions to help get them estimates of carbon emissions for specific disturbance types. And finally, we've been working with policymakers to help them understand how these new technologies could help us better define and measure degradation at an international level. Then we're looking to extend our own data set. So we'd like to create accurate pan-tropical estimates of carbon emissions from degradation, getting back to that uncertainty that we talked about at the beginning. We'd like to understand how different types of degradation are restructuring tropical ecosystems, including these interesting patterns in the understory and upper canopy. So that's all from me. Thank you so much. And please do get in touch, talk to me after, or here's my email.